Hello, Open XML developers. This is Eric White with the next screencast in a series of screencasts on writing recursive, pure functional transformations of XML. In this screencast, I'm going to examine the whole issue of laziness and eagerness. I'm going to examine this in quite a bit of detail. This is one of those topics that you very well may be familiar with if you are an experienced functional programmer, or you may not be familiar with this particular issue. If you do understand this issue, feel free to skip this video and proceed on to other videos where you don't understand the issue that I'll be presenting in those videos. This issue of laziness and eagerness is actually super important. It's what enables functional programming to really work in the real world, and it is also what enables recursive, pure functional programs to work in the real world. There are places where we explicitly want to control laziness and eagerness. There was one particular time where I was transforming a document that had 2 million elements and attributes in the main document part, and when I first wrote the transform, it took about 6 minutes to run. It was a very large document. It had about 6,000 pages of content in it. And at first 6 minutes wasn't too much, but after a while 6 minutes became clear that I wanted to have a transform that executed in less time than 6 minutes. And in that particular case, as it turns out, that I picked a particular place in the middle of the transform where I changed the characteristics of the transform from being a lazy transform to an eager transform, and my execution time for that transform went from 6 minutes to about 45 seconds, which was much better. I think the easiest way to explain the whole issue of laziness and eagerness is to demonstrate this in a bit of code. Here we have a small C# example program. This C# program is really artificial and it's artificially simple, but I wanted to make it this way so that I can demonstrate laziness and eagerness in the most obvious way possible. In this program up at the top here, I declare a source array of a number of integers, and then below that I have a query. And this query, first of all, dots into a .where. And in this .where, you'll notice down at the bottom of the .where, the bottom of that lambda expression, it always returns true. So this .where, it's going to result in the exact same collection coming out of it as what went into it. The only thing that this lambda expression does along the way is it prints out to the console each item as each item comes into that where extension method. And then I dot into another .where that has the exact same characteristics. It always returns true. So in other words, the resulting collection coming out of that second .where is always going to be the same as the collection coming into it. And then finally down here at the bottom, the code iterates through every item in the result, and it prints each item out to the console. It then puts a blank line after it prints each item to the console in the for each. So now if I run this example, we can see the first item 3 goes into the first where, and that item goes into the second where and gets printed, and then it finally gets printed in the for each. And then the code goes back and it gets the first item out of the source array, prints it in the first where, prints it in the second where, and then prints it into the for each. The problem is one of the garbage collector. If we didn't have this characteristic, let's say that each item didn't come into the first where, then to the second where, and then into the result. And let's say that our source array were, for instance, 20,000 or 50,000 items long, then what would happen is that this source array has been allocated 50,000 items long. It would go into the first where, and the first where would then also allocate another array of 50,000 items long, and then that would go into the second where, and that where would then allocate another array of 50,000 items long, and then finally we would iterate through that second array. And what this would do is this would put immense pressure on the garbage collector. That this means that this query would be allocating these huge arrays that are used just for a little bit of time and then discarded. And what happens is you could write little example programs, and these little example programs would work just fine. You could do this style of functional programming with these little example programs and write queries that were very easy to write and looked nice and so on. But then as soon as you started operating in the real world and you started operating, for instance, on that document that had 2 million elements and attributes in the main document part, in that particular scenario, the whole thing would allocate too much memory all the time on the heap, be freeing up too much memory on the heap, and the whole thing would come to a crashing halt. So certain of these operators, such as where, are intrinsically lazy, and certain of them are not intrinsically lazy. So you can certainly imagine that this where extension method, it's able to get the first item, decide whether it needs to be passed on out of that query. In other words, it applies the predicate to that item. And then if the predicate returns true, then it passes it on to the next part of the query. So where is intrinsically lazy, but order by is intrinsically eager. So what eagerness does is it has to collect every item in the source collection before it can sort them. This makes sense. The last item in the source collection might be sorted in such a way that it becomes the first item in the collection coming out of the order by. So if I come here and I dot into dot order by, and I'll order by the item itself, so I can write basically the identity lambda expression. So order by I arrow I. And now I run this example program. What we see is that we see every item in the first where before we see the first item in the second where. And then after the entire collection has been sorted, then the second where operates in a lazy fashion. So we see each item go into the second where and then go into the for each. And again, go into the second where, go into the for each, second where, and for each. This is called materialization. When you do some operation in a query that causes the query to now quit operating in a lazy fashion and now to start operating in an eager fashion, what you have done is you've taken a query and you've materialized it in memory. That's the nomenclature that we like to use for this particular operation in a query. There is an extension method that you can use that explicitly materializes. You can call .toArray. So when we call .toArray, this also is going to cause explicit materialization. So in this particular case, when we run it, we see every item being passed into the first where. We then see every item being passed into the second where, and then we see every item being printed out in the for each. So in the first case, in the order by, we caused materialization because we called an extension method that explicitly materializes, as order by must. And in the second case, we caused materialization by calling into an extension method that the whole purpose of that extension method is to materialize the collection. There are others that can materialize the collection in C#. You can materialize to a linked list by calling the toList extension method. You can materialize to a dictionary and so on and so forth. But the key point about this is knowing where you are writing parts of a transform that are lazy and knowing where you are writing parts of a transform that are eager is very important. Later on, when we start writing some more elaborate functional transforms, I'll be explicitly showing where I am materializing the query at some particular point in time, and at other places I'll be showing where this query is lazy, and this laziness actually gives us good performance profiles or a good performance benefit. So now we can go look at the equivalent characteristics in the JavaScript implementation of language integrated query. In C#, these characteristics of eagerness and laziness, they're baked right into the language and right into the .NET framework. What happens when you have a lazy method, or a method that operates on a collection in a lazy fashion? It uses things called iterators, and the iterator enables the code to, for instance, reset the iterator, get the first item, get the next item, and then there are operations that you can take in C# where you tell it to return an item into the next guy who's going to process that collection out of the first extension method. In the case of JavaScript, the laziness and eagerness are implemented in this link.js library. This link.js library is the brilliant link to objects implementation for JavaScript that is on Codeplex at linkjs.codeplex.com. In the link.js module, in that library, one difference between that library and C# is that in C#, an array of integers itself implements the interfaces necessary to process that array using language integrated query. In JavaScript, this is not the case. Instead, when we want to write a query on an array, we have to use this method enumerable.from and pass in the array that we want to operate on. And when we pass in that array, we get a collection that we can then dot into the where method or the order by method or the toArray method, and then we get the laziness and eagerness characteristics that we want. So in this particular case, this first example is exactly a parallel to the first example that we had in C#. So if I run it, we see the results in the browser where we see the value that is passed into the first where, the second where, and the for each, and so on. If I modify this and add the order by, I am also putting in the equivalent lambda expression for JavaScript as I had in C#, but of course I have to use the JavaScript syntax, which is a little bit different from C#. And if I run the resulting example, then we see the exact same thing that we saw in C#, where every item is first printed in the first where method. In other words, the materialization happens in the .order by, and then the second where and the for each are implemented in a lazy fashion. And same thing if I dot into toArray at the end of that query, we see the exact same results that we saw when we did the same experiment in C#. Key point about this is that the laziness and eagerness characteristics for JavaScript are basically an exact parallel to the laziness and eagerness characteristics of C#. So our thought process in designing our laziness and eagerness characteristics of our transform are the same for JavaScript and for C#. That's all I'm going to cover in this video. In the next one, I'm going to talk a bit more about extension methods and how extension methods fit into this whole scheme of things of writing these queries. We'll see that the mechanism for extension methods is different for C#. C# has this explicit notation to define extension methods, whereas the mechanism in JavaScript is completely different, but we get a similar benefit in the resulting code that we can write in both C# and JavaScript. So until next time, talk to you later.